Hello community, finally we're gonna code today again, and today we are here with vision transformers and diffusion models. Now, you know Stable Diffusion, you know Midjourney, our AI image generator, our text-to-image AI. And let's focus on Stable Diffusion. You know we can generate here high-quality images from textual description. The theory is here the physical process of diffusion, so theoretical physics are welcome here. And the training of the model is by a reversion of the mathematical diffusion process. Great, you know this. Now, today we're going to focus on something new and latent consistency models, which are distilled from the pre-trained latent diffusion models. And since last week, we have even something more interesting that is simply fast. We are talking about speed. We're talking about speed increase from 10 times faster. So instead of waiting 1 minute for your image to be generated, it is now done in 6 seconds. So, and this thing is called LCM-LoRA. And you say, hey, finally we have here the LoRA optimization also here on an advanced Stable Diffusion model. Yes, of course. So let us start now. At first, new type of technology, create images from text or simple sketches. Great. What makes LCM special is their speed. And they are a specific class here of our classical latent diffusion model. And they address here the computational challenges by transforming the reverse diffusion process into something more computationally efficient. The way this is done is, if you want, the core innovation is now the model's ability to predict the latent space trajectory of the reverse diffusion directly by bypassing here all the iterative steps. And they do this here by conceptualizing the reverse diffusion as an augmented probability flow ordinary differential equation problem. And I will show you here this in a second. It stands out for its remarkable efficiency, and I will show you when we code this, you get excellent results just with 1 to 4 inference steps. So with LCM-LoRA, we have now a universal training-free acceleration module that can be directly plugged into your various Stable Diffusion fine-tuned model or your Stable Diffusion LoRa's. Great. If you are not up to speed, here are my videos on the channel. You find here about before diffusion. You remember we had the variational autoencoders, then we had the vector quantized variational autoencoders. Here in this video, I coded with you here explicitly the complete thing from the variational autoencoders to unit to clip. And in this video, I explained here the interplay of these 3 elements, how we create the classical Stable Diffusion. If you're a little bit more advanced, beautiful, you know, there's this Stable Diffusion XL model. I introduced you here to the control net here of Stable Diffusion in XL. And of course, the control LoRA T2I, text-to-image adapter for here Stable Diffusion XL. And if you are into JAX, I have a video here about the TPU multi-parallel processing in JAX of Stable Diffusion. And we code this in this video. So this was the basics. Let's start. Latent consistency model, something beautiful. As you can see, again, Tsinghua University, China, October 6, 2023. This is something really, really nice. And there's one sentence in the whole publication I want you to remember. They view now the guided reverse diffusion process as solving an augmented probability flow ODE. So those LCMs are designed to directly predict the solution of such an ODE in the latent space. This is what we're going to focus on. Great. So if you're not up to speed, okay, one slide for you. Ben, this is for you. Diffusion models. You remember diffusion models? Those are generative models that progressively inject noise, Gaussian noise, into the data and then generate samples from noise via the reverse denoising process. This means diffusion models define a forward process transitioning the original data distribution to a marginal distribution via transitional kernel. In a continuous time perspective, the forward process can be described as stochastic differential equation. You say, yippee, yes! Here we also have our standard Brownian motion. Now, by considering the reverse time SDE, one can show that the marginal distribution satisfies the following ordinary differential equation called the probability flow ODE. This is important. So this is our baby here. This is our beauty that we're going to focus on. Now, in the diffusion models, we train the noise prediction model epsilon theta to fit here minus nabla log qt xt, called our score function. And approximating the score function by the noise prediction model, one can obtain now our empirical PF-ODE by sampling this. Beautiful. Then, for you, if you want to deep dive into this, you have to go to Appendix A of this publication. And you see here a detailed step-by-step explanation by all the steps we just rushed through. They are about, starting at page 12, about 4 or 5 pages where they tell you exactly how this is interconnected and how you can compute it mathematically. So if you are really into diffusion and consistency models, the Annex A, B, C, D is really highly recommended to understand this on a mathematical basis. Consistency model. Our consistency model, our CM model, a new family of generative models that enables one step or some few step generation. This is the beauty. So, core idea of CM is to learn the function that maps one point on the trajectory of our PF-ODE to the trajectory's origin. More formally, a consistency function is defined or can be defined here, our f, where epsilon is a fixed small positive number, and one important observation should satisfy the self-consistency property. Yes, 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 beautiful. And they have here a new technique. They have here the skip and the out methodology they introduce here, the authors. But remember, here our consistency model can either be distilled from a pre-trained diffusion model, and this is what we are going to focus on, or you can train it from scratch. So what we are looking now is consistency distillation. This is what is here the key to go then to LCM-LoRA. So to enforce the self-consistency property, you will maintain a target mode, theta updated with yes, 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 you know of this, yes, of course. But what we're going to focus on, yes, we recall that the PF-ODE of the reverse diffusion process is this beautiful little thing here. But what I want to show you is here where these solvers further, yeah, and we introduce here the skipping step technique as I already showed you. And now our LCM aims to predict the solution of our PF-ODE by minimizing the consistency distillation loss. And you know this from our AI system. We have a loss function and we minimize the loss function. This is it. So now we have reduced everything we know about here the distillation and about the latent consistency distillation LCD in the latent space. We reduce this to this simple minimization problem. Yes, beautiful. This is it. And then we have our ODE solver C, and you know all of this, you know several ODE solver, but this is now what we're going to focus on. Great. So, then for you, distillation loss is a key concept in model distillation technique used in machine learning to transfer knowledge from a large complex model, you know, our teacher model, to a smaller, more efficient model, the student model. This is exactly what we do here. So we have, where is it? Here. Now again, here we go. So we have here a big model. Where is it? Heaven's sake, where is our model? Here. CM can either be distilled from a pre-trained diffusion model. So we have here an LCM and an LDM. And this is exactly what we're going to do. We create now a student model, an LCM model that performs as closely as possible to our LDM model while being more efficient in terms of computational resources. Distillation loss is calculated, loss function I just showed you. Beautiful. Let's have a look at the efficiency, and you remember we have the guided distillation process. Now, This is more efficient. And the authors point out here, with the previous model, the guided distillation here, we have a two-stage distillation to support few-step sampling. Yes, yes, yes. Important to notice, we go from 45 days on an A100 with this new method, LCM, to 32 hours on an A100. So, wow. Creating, fine-tuning our LCM is now significantly faster. And this is what we're looking for. Yes, yes, yes. We need to solve now the following augmented PF-ODE. Beautiful. Now this is our beauty that we have to focus on. And yeah, it's the same as I just told you. Great. So now we have done our homework. Now we know where current research is. And now let's have a look what happened last week that suddenly from this point of the concept, we can now accelerate tenfold. And this is the publication, November 9th. So, almost 6 weeks later, we have now a new publication, also by Tsinghua University. And now, finally, we're talking about LCM-LoRA. So, a Universal Stable Diffusion Accelerator Module. Now, this is the problem, and they are now based on the Latent Consistency Model we just had a look at. We understand now what's happening, and now we optimize this. And there's, again, one sentence I would like that you focus on to understand what's happening here. So, since the distillation process of our LCM, of our latent consistency models, is carried out on top of the parameters from a pre-trained diffusion model, our LDM, we can consider latent consistency distillation, our LCD process, as a fine-tuning process for the diffusion model. And now you say, hey, we are now in fine-tuning and we know everything about fine-tuning. Because the last 2 weeks actually, I showed you in my video everything about here, the parameter efficient fine-tuning compared with RAG. And then we fine-tuned here a co-pilot here with a PF-LoRA quantization, everything here. So in our LLMs, in our large language model, you know exactly what we do. We go from the classical fine-tuning to the parameter-efficient fine-tuning, and from the portfolio of methodologies in PF, we choose one method, and this is our low-rank adaptation for here, our reduced matrix calculation. Beautiful. So we do now everything from the fine-tuning process of the last 2 weeks. Now we go to the stable diffusion process, to the LDM, to the LCM, and now we apply LoRA over there. This is it. It's as simple as can be. The complete mathematics has already been programmed for you. I know you wanted to do this yourself. I'm so sorry. So this is it. This is the complete code that you need to use now, LCM-LoRA. And this thing is 10 times faster than what you have till the time before last week. So you have here my notebook here. I have my pip install, transformer, PF diffusers, and accelerate. From diffusers, we have now our LCM scheduler, our diffusion pipeline. And you notice we have our stability eye, our stable diffusion XL base model. Whenever you see this, maybe you have a better base model than 1.0, go with what you have available. And then from latent consistency, we have now our LCM-LoRA SDXL model. Now, this is exactly what we are looking for. So what we do, we create our diffusion pipeline from our pre-trained model. Yes, we load now the LoRA weights here from our LCM-LoRA SDXL, our scheduler, beautiful. We push it to the CUDA device. And then we have here our prompt. This is our text. We say, hey, we want to create a close-up photography of an old man standing in the rain at night in a street lit by lamps, like a yes, yes, yes. And then we say, hey, pipe prompt, the number of inference step, the guidance scale, and create the image. This is it. Few lines of code. Now, you go to Hugging Face and you have there our LCM-LoRA SDXL. And as I already told you, Hugging Face decided now to have all the adapters listed now. So here, this is what I want to show you. Here, wherever you go here to an LCM-LoRA for example, SDXL, you have now here indicated, hey, this is an adapter, a LoRa adapter for this particular Stable Diffusion XL based 1.0 model. And this is now the interesting part, that you could choose now your adapter. Great. So let's run this program, and in just 4 inference steps, we get exactly this image. Look at this. 10 times faster than SDXL. And I think the quality for 4 inference steps is really extraordinary. Now, if you go, hey, I want to go to 8 inference steps. Well, it's not always that more is better. Look here. Here we have 1, 2, 3, 4. This is the image I just showed you. If you continue with more steps, 5, 6, 7, and 8, it depends. If you like it, go with it. But you see, even 4 steps give you, 2 to 4 steps give you a really good image generation. And this is blazing fast with LCM-LoRa. Great. If you say now, I have this model and I want to check now back to my original performance. So what you do, easy. You see here in your pipeline, hey, I unload the LoRa weights, delete it, get rid of it, go to my scheduler, load here the classical Euler discrete scheduler. So we revert our pipeline to a standard SDXL pipeline by unloading the LoRa weights. We switch to the default thing, and then we need much more steps, inference steps. And so let's have a look here now at the outcome if we go from 1 step, 4 steps, 8 steps to 50 steps. You see, just some line of code, couldn't be easier. And here you have it. So step number 1, the classical SDXL, just noise, of course. 4 steps where we had already with LoRa, with LCM-LoRa, here the perfect picture. You see it takes here, look at this horror here. It takes 50 inference steps till we have a comparable quality. So this is the benchmark. Here we need 50 steps, and with LCM-LoRa we just needed 4 inference steps of our LCM model. And this is the beauty, how LCM are now so blazingly fast. But remember, we have to create them from our LDM model. And it takes about, I don't know, was about 30 hours on an A100 to create those LCMs. So if you have a beautiful model and you want to optimize this model, it takes about 30 hours on an A100 to generate here the LCM. So you have this once, but if you have this model created once, you can use it 100 and 1,000 times to create here all your images. Beautiful. In this presentation, in this scientific paper, there's something else that is really beautiful. And you will have immediately that you see there's a parallelism compared here to our multi-LoRa adapters in our large language model. And as you can see here, we have here a combination of a multi-LoRa adapter. We have here our base LDM with that base, and then we create here our LCM-LoRa. Beautiful. This is blazingly fast. But if we want to add additional LoRa adapters, as I showed you in my last video, to LLMs, we can do this now here too. We create here now a customized LDM, theta dash, with what the authors call here a style vector, and the pure LCM-LoRa they call an acceleration vector. And if you have 2 vectors, you can combine 2 vectors with a linear combination, and then you get a customized LCM theta dash. This is now nice because now we have 2 LoRa adapters that at first we have our LCM, but then we have a style adapter. Let me show you this in code. Look, we combine now our very fast LCM-LoRa accelerator vector with the style vector. So here we go again. From diffuser, Hugging Face diffuser is now in the latest version. Please update to the latest. We have now our LCM scheduler. We have our diffusion pipeline. We go again with Stable Diffusion XL base 1.0. We have floating point 16. Yes, beautiful. We push to the CUDA. Yes, and now comes the beautiful new step that we have in addition here. we have the LoRa parameters obtained through our LCM-LoRa training, what they call the acceleration vector, can be directly combined with the other LoRa parameters from a style vector by fine-tuning now this on a particular style dataset. So let me show you this. It is absolutely identical to the LLM, what we do now here in Stable Diffusion. You load your LoRa, and we have here at first here, as I showed you in the last time, the latent consistency. They have here the LCM-LoRA SDXL, and we call this LoRa adapter, whatever you like to call it, we call it LCM. And then you call here a style model. I will show you in a second. Auto was the last pen, and it's called PF-ODE SDXL. And you give it a name, and then you combine the LoRa's with this simple command. Pipe.set the adapters, and now you have your first LoRa adapter in combination with the second LoRa adapter, and you define the adapter weights. And this is it. And your prompt is now, hey, create a beautiful image, a paper cut image, and the object is a cute looking fox. Great. Now again, as I told you, on Hugging Face, you find here all the different adapters for Stability AI for the Stable Diffusion XL base model. And we take now another adapter from Hugging Face, go there, find the adapter you like or create your own adapter, and then use it in combination with the LCM-LoRA acceleration vector. And what you get out if you execute this simple line of codes is here exactly, you have here a cute fox, very fast, 10 times faster than the normal SDXL. So we utilize here the LCM-LoRA SDXL model, plus we give it now a style. We can now modify it according to our wishes. And this style has been fine-tuned here by this organization or person, and it is called PF-ODE SDXL, and this is now the fine-tuned style that all our models will have. Choose another style model, go with futuristic, go with some sketch illustration, whatever you choose. You see how easy it is now to adapt this with our LCM and the style adapters. So exactly as in the large language model where we have multiple LoRa adapters, now you can do this here also in Stable Diffusion. What a coincidence that it happens now also here on the visual sector. Okay, LoRa parameters obtained through our LCM-LoRa training. The accelerator vector can be directly combined with other LoRa parameters like the style vector obtained, where the style vector has been obtained by fine-tuning on a particular style dataset. You have, I don't know, 100 images or 1000 images of a particular author, of a particular artist, and in a particular style you like. You simply do a fine-tuning of the adapter, and then for the inference, you just click in the adapter and it works. It's gorgeous. So without any training, and please, this is what I like to stress, without any training, the model obtained by the linear combination of the accelerator style and the vector style acquired the ability to generate images of a specific painting style in minimal sampling steps. Yeah, this is the beautiful formulation. So what we have, compared to the previous numerical PF-ODE solvers, such as, you know this, where you have your click down menu and you go for a solver. Now the new LCM-LoRa can be viewed as a plug-in neural PF-ODE solver that possesses strong generalization abilities. Beautiful. This is the official marketing. Great. Now, what I find particularly interesting, you know, we had with Stable Diffusion XL, we had LoRa's. Of course, it existed before, but those were the very slow LoRa's. Now, with our LCM LoRa's, our ultra-fast LCM LoRa's, we can combine this. And this is the unbelievable thing of adapter synthesis. Look, we use here, yeah, of course, latest update, code update, Hugging Face diffusers, and the latest PF-ODE version. Please update before you do this. You can combine your LCM LoRa's, the brand new ultra-fast LCM LoRa's, with your regular, slow-moving Stable Diffusion XL LoRa's, giving them now in total the superpower to run LCM inference in just 4 steps and not 50 steps or 100 inference steps. Beautiful. Let's have a look at the code. It is so simple. Again, our LCM scheduler, we go here with our LCM-LoRA SDXL. Beautiful. You load the weights and great. And now you say, how do I have to reconfigure the system to integrate here our regular SDXL LoRa's? You're not going to believe it. There too on Hugging Face, you remember, an adapter for Stability AI Stable Diffusion XL base 1.0 mile. You choose now an adapter for a particular style. And this particular style, yeah, don't ask me why, it's a toy face. Beautiful. I don't care. You create your own adapter. You choose your adapter from Hugging Face. Do whatever you like. But it is an adapter, and we use this standard LoRa SDXL adapter that has not been optimized for LCM-LoRa. And look, we just load here the LoRa weights from this non-LCMM. Give it a name. It's called toy. Beautiful. So now we have our pipeline. We set the adapters, 2 adapters, our LoRa adapter, our LCM LoRa, and our non-LCM LoRa, our toy adapter. Push it to CUDA. Say, hey, our prompt is, well, you're not going to believe it, a toy-faced man or woman or animal or whatever. You can have your negative prompt if you like it, and this is the command. You see, just some lines of code, and you get exactly here. You can combine if you created your own classical LoRa's for your SDXL, you can still use them and get the speed increase if you just add here this line of code, our LCM-LoRA SDXL. Please note that the quality of this is highly dependent here on your model, on your LCM-LoRa conversion here, as I just showed you, and of course on the quality of your standard SDXL LoRa's. There's a lot of optimization going to happen, so please take care that you have the perfect model. Great. Yeah. As I told you, the style vector, you can create your own style vector by fine-tuning a base model on a data set, 100 images from your particular scientist or whatever you have, a visual artist, present a specific style or type of imagery, yes, yes, yes. Encapsulate the characteristics, yes, I just showed you, and the pure and the beautiful power here of our LCM-LoRa comes into play when we use this combination of the accelerator vector and the style vector. I showed you this is simply the mathematical operation, a linear operation, and you have some hyperparameters to balance it, the contribution of each vector. This is identical to our alpha vector that we have to augment our LoRa adapters if we have multiple LoRa adapters in our large language models. If you decide now, hey, it's time to learn more about multi-LoRa adapters here, you can go to my channel. I explain here LoRa, I explain here 4-bit quantized LoRa. I have here RAG and PF and optimized PF LoRa. And of course, here the last one is PF on multi-LoRa explained with explicit LLM fine-tuning. And if you want to have here the latest here, this is my video where I showed you adaptive tuning with PF and LoRa for new LLMs, that there's a new methodology out now. But I have also a complete playlist of 13 videos about adaptive tuning with PF and LoRa for language models. And now in this video, I showed you we can do it now also for stable diffusion. And if you're into this, here you will find here the next step that will happen in optimization. Because it happened here, and this is S-LoRa or scalable LoRa. And we have here in a multi-LoRa adapter environment, I showed you that the authors here in this video, I presented you this, that here with S-LoRa, we have 3 significant optimization, but not now of the minimization problem of the stable diffusion problem, but here now in the pure compute infrastructure. And I showed you here with the S-LoRa, and we have also the multi-LoRa here in the diffusion model. They optimized it here with a unified memory pool for adaptive weight tensors and a key value cache, minimized the latency when batching here different LoRa adapters, and they invented here a new tensor parallelization when computing here our tensor multiplication. So there's now an optimized GPU, NVIDIA GPU kernel optimization for a better mathematical operation of the tensor multiplication. And this has given here in the LLM significant speed improvements. But this is the next step that's going to happen now in the Stable Diffusion, because this implementation of those three measures that gives us, compared now to our VLLM inference, a 400% performance boost. This has not been implemented yet at the Stable Diffusion level. So you see, the research transfer, the knowledge transfer from the optimization here, from the LLMs here to the Stable Diffusion or to the visual has not happened yet. But knowing this from the LLM side, we can say, hey, and the infrastructure optimization here from CUDA kernels, from unified memory pool, for going from the simple page detention here to here a unified paging, reduce the memory fragmentation, optimize the memory management in total now for our different LoRA adapter layers. There's still a lot that can be done, and this will be the next step here in the research for the Stable Diffusion optimization problem. Wow, I think this is it. I hope you enjoyed it. You have an idea how simple it is to code this. Go there, take your example, just get familiar with it, and be amazed about the speed increase. For my things and for my models, it was 10 times faster, sometimes even 12 times faster in the generation of the image, given I have some simple text expression. What I did not test out myself, you can also have here an input to the model by simply sketching here some basic sketches, and the model will do here the complete formalization. Yes, you can do also in painting here with those LCM-LoRA adapters. So in the next week, I think you will see a lot of new examples about LCM-LoRA for Stable Diffusion. But now this is it for this video. I hope you enjoyed it. I hope you had a little bit fun. I hope you learned something, and it would be great to see you in my next video.